Hi there. Welcome to our presentation on PaReprop, fast parallelized reversible backpropagation. This is joint work between myself and Kartikaya Mangalam at UC Berkeley. Our motivation is based on the recent dominant trend in machine learning of creating larger models for easy performance boosts, as this greatly amplifies the impact of small speedups and efficient implementations. So as models scale up, how can we make more general and memory-efficient architectures? One such possibility is to use reversible transformations. Their key property is that we can perfectly reconstruct inputs from outputs. This relies on having two functions f and g, which crucially need not be analytically invertible. As illustrated below, we have our forward pass here on the left, and we show the very simple method of recovering the inputs from outputs on the right. One recent work which uses these is reversible vision transformers, published last year at CVPR. They extend reversible transformations to transformers by setting f of x to be the attention block and g of x to be the MLP block. In this way, we can ignore the activation caching in the forward pass and simply recover them in the backward pass instead. They show that doing so achieves equal performance to the vanilla method and at the same flops and parameters used, also uses less memory per image. Now, let's discuss the backpropagation here in detail. Illustrated here is a typical backpropagation. In blue, we have the forward pass of every single block, and in orange, we have the backward pass where we update our gradients. And as you might expect, during our forward pass, our memory usage increases as we need to cache the activations, whereas for each corresponding backward pass, we release that activation memory once we are done updating our gradients. Compare this with reversible backpropagation. Now in our forward pass, we no longer need to use any memory to store these activations. However, this is now deferred to the backward pass, which is demonstrated here in these new green blocks here. These green blocks recover the activations in the backward pass before doing the typical backward pass for gradient updates in orange. However, notice that the maximum amount of memory used at any point in time is still much lower than that of normal backpropagation. However, there is a key detail here, which is that there is no dependency between these two blocks. For example, once I recover the activations of block 1, I can both update the gradients of block 1 and recompute block 0's activations at the same exact time. This inspires our method, PaReprop, Parallelized Reversible Backpropagation. Our insight is to run both of these in parallel, since once we have the activations, we can do both steps at once. And this will speed up our backpropagation significantly. And while I've only talked about vanilla vision transformers, we also benchmark our method on a variety of architectures, such as multi-scale vision transformers and reversible swim transformers. Now, first we see that PaReprop improves throughput on all these vision architectures, ranging from different classes such as vision transformers and MVIT to different sizes as well. Most notably, here we can see PaReprop, shown with the blue stars, is much better than both of these hierarchical architectures in MVIT and SWIM, compared to reversible propagation, which is highlighted in orange squares. This is a general trend which we find, which is that PaReprop has the largest gains for hierarchical vision transformers, achieving up to a 20% speed up in throughput on SWIM giant models. This, we hypothesize, is due to their non-homogeneous nature, as they have many small operations which are especially amenable to parallelization. We find that our method is also good for language models, testing this on a reversible Roberta implementation that we came up with, while testing on both base and large sizes and two different sequence lengths. We also find that the memory used is negligible. We compare the memory across all three of these different methods, and we find that typical backpropagation uses the most memory, and using any kind of reversible backpropagation saves us a ton of memory. Therefore, while we do incur a slight memory cost using PaReprop, this is negligible compared to the overall savings used by any reversible propagation. In conclusion, reversible architectures offer extremely memory-efficient training at the cost of some recomputations. PaReprop essentially negates them by parallelizing the backward pass, and in practice, PaReprop performs on par or better than reversible propagation, even reaching up to 20% speedups in throughput compared to 25% theoretical maximum, being especially good with mixed architectures like hierarchical vision transformers. And check out our poster for more details. or look to our linked website below or the QR code. Thank you.